So we're going to talk about file security and permissions for a little bit to understand sort of the fundamentals of security in Linux. So we'll just introduce a few concepts, the notions of users and groups, just sort of understand a little bit more about those. Then we'll get into talking about file and directory permissions, how they work, how you interpret them. So they work a little bit different depending on whether they're applied to a file or a directory, so we'll understand that. And then I put some exercises into the end of the lecture just that you can work on at home to sort of solidify your understanding and also to help you in your midterm study. So first things first, users. So we talked in the first topic in this course about accounts or users. So a user is an account that allows either a person or a system entity, a process, to interact with the system. So I can create a user account for you, give you the password, you can log in and work with the system. In the same way, I might want a particular program that's running on my computer to only have a specific set of privileges. Maybe I only want it to access certain directories. So I will create a user account for that program and run it under that account. And that way I can give it whatever permissions it needs and sort of restrict things for it. Now, each user has a unique ID known as a UID. And local users are stored in a file called /etc/password. So you can see the format there. You've got everyone's username. Then you have this X. So it used to be that back in the day, everybody's password hash, right? Passwords are not stored in plain text. They are stored hashed so that someone can't just open up the file and read your password. So back in the day, all of your password hashes were stored in etc password, and they were stored in this second column here. The problem with that is that even if the password is hashed, if I'm able to access that file, it makes it easier to attack your password. I can start running automated password cracking tools that try out different passwords and then compare them to your password hash, and then that makes it easy for me to crack your password. Now, problem here is that etc password has to be accessible to everyone on the system because processes, for example, like ls needs to be able to look up user information in the password file. So when I type, ls-l, it's showing me the username and the group name that owns each file. It has to look up that information by referencing the password file, so it has to be publicly accessible to all processes. So they said, okay, we're going to take these passwords out of this file, and we're going to move them into a file that is only accessible to root called etc shadow. Okay, so that's why there's that, it's a long-winded explanation for why there is an X there that used to be where your password was stored. So we got your username, former location of your password, then you have your numeric user ID, your UID. You have your GID, so your primary group ID, the ID of your primary group, and we'll talk about that in a minute. You then have what's called the geckos field. It's a historical name, but it's just basically it stores your user information. So generally your full name. You then have your home directory and, of course, your shell. So when you log in, SSH is going to look at the password file. It's going to see, okay, your shell is /bin/bash, and then it runs bash for you, and now you can work at the bash shell. Same with, when I type like cd // cd is looking at the password file to translate that tilde into the path to your home directory. Okay, these aren't magic things. It's getting this information out of the password file. Now, I should note that if you go on Gall and you look at the password file, you're not going to see my user account. You're not going to see your user account. That's because these are only local users. You can also have a remote user server, as we do, that stores other users that your system can also use. Okay, so for example, all of the student accounts are stored on a remote server that our system accesses. If I wanted to see my password entry, I can use this command getEnt. So get entry from the password file and then my username. And now that pulls up that information from the remote user server. I see my UID, I see, my username, my UID, my GID, geckos field, home directory, and my shell. Okay, so groups then are collections of users, and they are used to simplify things for your administrator. Okay, so rather than having to worry about, okay, I'm going to assign these permissions to you, and these permissions to you, and these permissions to you, I can create a group, put you all in the same group, and then assign permissions to that group. So maybe I grant access to read and write to a given file, and I grant that access to a particular group of users. And now I don't have to worry about finding a way to grant all of those users individual access to that file. So same with etc password. Local groups are stored in etc group, and you can have groups stored remotely on a separate server. But if you take a look at etc group, you'll see all the local groups. Now, format is similar. So we've got the group name. We've got an X. So this is actually the group password. You can have a group password. It's not used really anymore. It is a security risk. It allows people to basically temporarily join a group by typing in a password, and it's just considered to be a risk. So usually this will just be an X. Then you have the group ID, so a unique identifier for that group, and then a comma-separated list of the group members. So you can see the students group there has 2 members, Joe and Zoe. Now, we also have the notion of a user private group. When you create a user on a Linux system, not only does it create your account, so if I create a user Joe, it creates the account Joe, but then it also creates a group called Joe, and it makes Joe's primary group ID, his primary GID, the ID of that group. So you can see here it created a group Joe with a GID of 5,000, and if we look at the password file, when we created Joe, it put Joe into the Joe group, right? Group ID 5000. Now, the reason for that is, so this is called a user private group. And the reason for that, well, I guess we'll see in a minute, but it basically means that when I create a new file, by default, it's going to be owned by me, and it's going to be group owned by my user private group so that nobody else can access that file unless I explicitly allow them. Okay, so that's just a convention on Linux. You will often see groups with the same name as the user. It's called a user private group. Okay, so permissions are sort of the fundamental building block of Linux security. They control access to every file system entity. So every entry in the file system has what we call a mode. It has a set of permissions that control access to it, whether it's a file, a directory, a link, whatever. They all have a mode. And of course, ensuring that we have proper permissions, helps us to maintain our security. It helps us to prevent unauthorized people from accessing files they shouldn't be, prevents sensitive data from being leaked. I can lock it down so that only I can access it or only a group of users can access it. Maintain my system integrity so that people can't, for example, go into /user/bin and put a malicious version of the ls command in there so that whenever somebody types ls, it deletes all their files or infects them with a virus or whatever. And yeah, just in general prevents malicious activities from occurring by keeping things locked down. I mentioned that every file system entry has a mode, a set of permissions, which is stored in its inode. So you can see here an example inode. It's got a mode of 0644, and we're going to learn in this topic what that means. But just know for now that every single entry has its mode stored in its inode. So it has its set of permissions. Now, with respect to a file's mode, Linux will divide up the set of all users on the system into 3 groups. We have user, group, and other. So the user is the owner of the file. So when you create a file, you become its owner. And so we have a set of permissions for the user. Root is able to change the ownership of a file. So, if you create a file, I can change the ownership to somebody else if we need to. By default, though, you cannot. It has to be the root user that does that. So we have user, and then we have group. So when you create a file, your file by default is group owned by your primary group. And in the case of Linux, it is your user private group. Once again, can change the group owner of a file, but again, you have to be root. They can use the chgroup command, but you can't do it yourself. So we have user and group, and then we have other. So other is just everybody else on the system. Now, we've already seen this, but when you type ls-l, that allows you to see the permissions on your files. So if I do this, this first column here is showing me the permissions on all of my files and directories, in other words, the mode. This column here is showing me the user owner, what user owns it, and this is showing me the group owner, what group owns that file, okay? And of course, this is my user private group. Now, interpreting the mode. So when you look at that string of bits, the first bit is going to be the file's type. So if you see a dash there, that just means it's a regular file. If you see a D, it's a directory. L is a symbolic link. So you can see we've got regular files here, we've got a directory, we've got a link. In this case, we have a pipe and a socket. So there are a few others, but generally you're going to see dash for regular files, D for directories. Now, the next 3 bits are the permission bits for the user, for the owner of the file, okay? And RWX stands for read, write, and execute. And we're going to understand what those mean in a little bit, but just know for now that the next 3 bits are for the user, and then we have the next 3 bits for the group owner, so the group owner of the file, and then the final 3 bits are for everybody else on the system. So in this case, this is saying that, all right, for the owner of this file, for jchance4, he can read the file, he can modify it, he can execute it. For the CS user group, so for anyone that is in the group CS user, they can read it and execute it, but they can't modify the file. And then for everybody else on the system, so not the owner and not members of CS user, they can read the file, but they can't write it or execute it. And of course, if we see a dash, that means that that permission has not been given to that particular user or group. So there's 2 ways we can specify permissions, octal or symbolically. So taking a look at octal first, you can represent all of those permission bits succinctly as a 3-digit octal number. So what you do is you take those symbols, so read, write, execute, we want read and execute for group, we want read for other. You convert them to binary. So wherever a permission is to be granted, you put a 1. Wherever it's not to be granted, you put a 0. And then you simply convert those groups of 3 into octal digits. So we have 111, which is 7, 101 is 5, and 100 is 4. And so in this case, you can represent those permissions with 754. Another example, we want to give read and write to the user. So that is going to be 110. Converting that to binary, that's 4 plus 2 is 6. We want to give read to the group. So that's 4, 100. And then we want to give no permissions to other. So that's just 000, which is octal 0. So that becomes 640. Now, to actually change permissions, you use the chmod command. Okay, so as another example here, I want to grant read, write, execute to the user. I want to grant read and execute to the group, and nothing else to anyone else. So I'm doing 111, 4 plus 2 plus 1 is 7. I'm doing 4 plus 1 is 5, so 7, 5, and then 0. And then that gives me that mode. Okay, another example here, if I wanted to lock down README, so that only I can read it, nobody else can read to it or write it or execute it, then I'll say chmod 600. So I'm giving myself read, which is 4, write, which is 2, so 6, and then 0, 0. And that locks it down. Now another way, and I remember when I started on Linux, this was certainly the easier way to sort of wrap your mind around, so feel free to use either or. If one makes sense to you, great. If the other makes more sense, perfect. They are both equivalent. This just requires a little more typing. So this is the second way you can specify permissions symbolically. And so the way we do this is, you again say chmod, but this time you can say, okay, I want to set a permission for the user, group, other, or for everyone, for the user group and other, in which case I would use A for all. And then I can either add permissions with plus, revoke them with minus, or set them with equals. And then I specify the actual permissions. So, example here, if I want to grant read, write, and execute to the user, I say chmod u plus rwx, add read, write, and execute for the user. If I want to add it for the group, I would say chmod g plus rx, give them read and execute permissions. If I want to revoke, I'll use minus, so remove read, write, and execute from other. If I wanted to give everybody execute access, chmod a plus x, all granted the execute permission. And then if I want to set the permissions for a given set of users, I could say equals. So chmod g equals r. So what that will do is, if I use plus, if we have a group that for some reason has write access to this file, but they do not have read and execute, all right? If I say chmod g plus rx, then that is going to grant read and execute, but it's not going to take away their write. If I wanted instead to say, okay, well, I only want the group to have read access and I want all their other bits cleared, then I can say chmod g equals r. And then that will just give them the read bit while taking away the rest. Okay, so plus was adding, but not touching existing permissions, whereas equals is basically overwriting your permissions and saying, all right, we want to clear all your permission bits and only set them to whatever you've specified here. And then finally, you can combine multiple with commas. So in this case, I'm saying, all right, we're going to grant read, write, execute to the user. We're going to take away write from the group, and we're going to remove all permissions from other. So you can separate them with commas that way. Okay, and this is just saying what I've just talked about. So both of these examples are equivalent to each other. So I could say chmod 7500, or 750, I should say, or I could have that big long string if I wanted to. Same with chmod 600, to lock down readme, I could say it this way instead. Grant read and write to myself, revoke read, write, execute from group and other. So whichever makes more sense. Again, as a beginner, this is probably easier. The symbolic way is easier to remember. But eventually you start to just understand what the different octal numbers mean, and then you're just able to kind of whip it out quickly, and it's a little bit less typing. So chmod changes permissions on files or directories. If we want to recursively change permissions, we use the -R option. So in our first example here, we're saying add the read and write permission on all files and directories under the given subdirectory. So read and write, but not execute. Second example is going to recursively grant read, write, and execute to everyone under directory, but it's going to make every single one of our files executable. Now, last day, one of you asked the question after class, what does it mean for a file to be executable? So let's just quickly explore that. If we have our little Hello World program, now, when we compile it with GCC, you will see that GCC automatically adds the execute bit for us. So it makes that file executable. If we were to take away that permission, so now it's no longer executable by anyone. And if I try to execute it, the shell says that it's permission denied. Okay, so it needs to have the execute bit in order to be able to run it. Same thing with a script. So if I wanted to write a shell script, we're going to look at shell scripting a little later on in this course. Don't worry about this line for now. It's just called the shebang line. It tells the shell what is going to interpret this script. In this case, it'll be bash. And so I could put commands in here saying, you know, my username is who am I? The date is date, for example. Now, if I want to be able to run that, once again, it needs to have the execute permissions set on it. So we'll say plus X, and now it is executable, so I can now run it, and it executes those lines that I put in it. Okay, so that's what it means to execute a file. Now, the problem with doing something like this, chmod a plus x on my directory A. So let's just look at our tree first of all. We've got this directory A. It's got a subdirectory B with some files in it, F1, F2. We've got a hello.c file, which clearly is not intended to be an executable file. You can't directly execute a C file. So the problem with doing chmod -r a plus x on our A directory is that if we now look at all of our files, you can see that they have all been made executable. Okay, so F1, this was just intended to be like a normal text file. Hello.c is C source code. It's not directly executable. So if I try to execute it, well, let's find out what it's going to do. It's just going to say syntax error because it's trying to execute it as a shell script, but it contains C code, so Bash doesn't know what to do with the lines in there. So clearly this is not ideal. A plus X is not ideal. So let's remake this structure. And this time, so we're back to how we were before. We have a script that is executable by other. It is not executable by group, and it is not executable by user. Okay? And then we have two files, F1, which is not executable by anybody. And if we go into B, we have another file that is not executable by anyone. And so we want, ideally, for those to remain non-executable. So what we can do is say A plus capital X. And what that will do is any files that were already executable by at least one of the groups, user, group, or other, since we said A plus X, all, it will then put the execute permission on the rest of them. Any files that were not executable by anyone remain non-executable. Okay, so that's the plus capital X. Now, default permissions in Linux. By default, any new files you create are going to have permission 666. So 666 is going to be read, write, and no execute bit, read, write, no execute, read, write, no execute. Okay, so that's default for files. And then the default for directories is going to be 777, which is going to be read, write, execute, read, write, execute, read, write, execute. We'll see what the execute bit means in a little bit for directories. But for now, just understand that these are the defaults for directories and files. Now, if we want, we can further restrict the default permissions that get applied to the files and directories we create using a command called umask. So this allows us to mask out, or in other words, unset permissions that we don't want set by default. So the chmod command, we're telling it what permissions we want to apply to a given file or directory. With umask, we're saying what permissions we don't want applied to a new file or directory. And on most systems, if you run the umask command, you'll see, we won't worry about this leading 0 for now. You'll see that the default umask is 022. So that masks out some permissions for group and other. It masks out no permissions for user. And if we wanted to, we could set an even more strict umask like 077, which would mask out all the permissions for group and other and no permissions for us. So to see what I'm talking about here, so again, we're saying that the default permissions that are applied in Linux to new files are 666. So read, write, read, write, read, write. Everyone can read a file. Everyone can write to a new file that you create. Obviously, that's not ideal. You don't want everyone on your system to be modifying a new file that you create. So that's where the umask comes in. So we take our default permission, 666, we convert it to binary. So 4 plus 2 is 6. And then we just repeat that. We take our umask, we convert it to binary. So 0, 2, 2. Okay? We then flip the bits, take the complement of the umask. So I've just flipped those bits there. and then we AND it together with the binary representation of the permission 666. So 1 and 1 is 1, 1 and 1 is 1, 0 and 1 is 0. So that gives us 4 plus 2 is 6. And we have 1 and 1 is 1, 1 and 0 is 0, 0 and 1 is 0. So that gives us 4. And then same thing here. So the result is that the default permissions, when you have a UMask of 022, the default permissions are actually going to be 644 for a brand new file. So in other words, read and write, right? 4 plus 2, read and read. So everyone on the system will be able to read any new file that I create by default. I will be the only one who can read and write it. Okay, and we can see that if I do, so again, UMask by default is 022. If I create a new file and we look at it, you can see the default permissions. I have write access to it and read. Everyone else has read. Now, I can further restrict that, obviously. I could say like chmod 600, and that would take away all permissions from everybody else, leaving me with only read and write. But by default, it's going to be read for everybody. Now, for directories, same idea. So we said that the default for directories in Linux is 777. So read, write, and execute for everyone. So once again, we take that, we convert it to binary, which is all ones. We take our UMask 022, convert it to binary, and then we flip the bits. And then AND them together. So 1 and 1 is 1, 1 and 1 is 1, 1 and 1 is 1. That gives us 4 plus 2 plus 1 is 7. 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1. That gives us 4 plus 1 is 5. And then same thing over here. So 7, 5, 5. So read, write, execute for the user. For everyone else, read and execute. And again, we can see that if we make a new directory, we have read, write, execute, and then for everyone else, read and execute. Yep. Sure. So if we unset our UMask, so I'm not going to mask out any permissions, okay? If I create a new file, that new file has been given read, write. So it's been given 666 permissions. So everyone on the system can read and write that new file by default. If I have a UMask of 0, so I'm not masking out any permissions. Similarly, if I create a new directory, that new directory, everybody has read, write, and execute on that new directory because it's 777 by default. So the UMask is saying, okay, no, we want to further restrict things. We want to mask out some permissions when we create a new file or a new directory. So instead of applying these Linux defaults of 666, 777, it allows us to further restrict things so that I can say, okay, no, I don't want to allow group and other to have write permissions to any new files that I create. So I'm going to mask those out by removing those permissions. Okay? And then again, we can further restrict things by saying, all right, no, I'm going to make my UMask 077. So what that's going to do is it's not going to mask out any permissions from the user, but it's going to mask out every single permission from group and other, because 7 is 4 plus 2 plus 1, right? Read, write, execute. So it's going to mask out all those permissions. So if I create a new file 3 now has no permissions for group and other, and it's got read, write for me. Similarly, if I create a new directory, we have no permissions for group and other, and we have read, write, execute for the user. Okay, so that's the UMask command. Again, it allows you to further restrict the permissions that get applied to new files and directories that you create. So generally, if you wanted to restrict things further, again, the default on Linux is 022. If you want to restrict it further and make it say 077, you would take that UMask 077, you'd put it in your bash RC, and then you never have to set it again. It will automatically be applied to all new files and directories that you create. So let us look at how to interpret permissions. So the way we interpret the different permissions, read, write, and execute, differs depending on whether it's a file or a directory. So for files, it's fairly straightforward. If you apply a read permission to a file, that means that someone is allowed to read the content of the file. So they could type cat and they can cat the file. They could load it up in an editor and view it, at least in read-only mode. So in order to read the contents of the file, you have to have the read permission. Write permission, of course, is required to change the file, to modify the file. So if I want to be able to edit the file in say Vim and then save the changes, I need write permission to it. If I want to be able to say overwrite a file with the CP command, I also need write permissions to it to change its content. And then finally, as we saw, in order to execute a file, whether it's a program or a shell script, we need the execute permission set on it. Now, directories are a little bit different, but they make sense if we recall that everything in Linux is a file. Directories are files. If you remember, directories have an inode, and that inode points to the directory's file on disk. And that directory's file on disk contains a table that maps all of the file names in the directory to inode numbers. So if you think about it that way, if you keep that in mind, then these permissions make a little more sense. So the read permission, for example, you need that in order to list the contents of the directory. In order to type ls and actually see the contents, you need read permission on it. Now, to understand why, again, we remember that the directory is a file on disk. In order to read the content of that file, in order to get that table and read all of the file names in it, we need read permission on it. Same with write. So write permission is going to be required to create new files. So in other words, to add entries to that table, to that file, to delete files from the directory. So to remove entries from that file. And then of course to rename files in the directory. So to change existing entries in the file, you need write permission. So if I want to RM a file, if I want to MV a file to rename it to some other name, I need write permission on the directory. Execute then is sort of a little bit, well, it's not hard to understand, but it's just a little bit different. So execute is required to traverse the directory, to get into the directory. In order to get access to one of its files or its subdirectories, I need to have execute permissions on that directory. So if I want to cd into a directory, I have to have execute permissions on it. So just to solidify things here, here's an example where, okay, we've got this directory structure. We have this directory dir. We have read, write, execute for the user. Group has execute but no other permissions, and other has no permissions. Within dir, we've got a subdirectory public HTML. Again, user has read, write, execute. We've got group with read, execute, and other with read, execute. And then we have this file, readme, where user has read, group has read, other has read, write, execute. So based on these permissions, the owner of the directory dir is able to list the contents of the directory because they have the read permission. They can also write files into that directory. So they can create new files, they can delete files, and they can rename files because they have write permission to the directory. And then of course they can change to the directory, they can cd into it because they've got the execute permission. Now, you can see that dir is group owned by the CS user group. So members of that group can change to the directory, they can cd into it because they've got the execute permission, but they cannot list the contents of the directory because they do not have the read permission. So they can't type ls. If they type ls, it's just going to say permission denied. Similarly, they can't change things within it. So they can't create new files, they can't delete files, they can't rename files because they don't have write permission to the directory. So they can get into the directory because they have execute permissions, but they can also read the file readme because they're able to get into the directory. They have read permission on the file readme, so they can, if they know the file name, if they know that there is a file named readme in that directory, they can cat that file. They just can't type ls to see that it's there, but if they know it is there and they type cat readme, they're able to get in the directory and they're able to read the file, so that will work. Similarly, they can change to public HTML. They've got the traverse, they've got execute on the dir, and they've got execute on the public HTML. So they can traverse past directory to get into public HTML directory, into the public HTML directory, I should say, because they've got execute on both. And then finally, all other users on the system have no permissions here. So they can't get into this directory because they don't have the execute bit, and they can't access any of the files or subdirectories. So even though we've given them read, write, execute on README, we've given them read and execute on public HTML, they cannot get access to those because we have not given them the execute bit, the traverse bit. So they can't get into dir in order to get access to any of its files or subdirectories. So I have put some exercises in here for you. I recommend trying them at home just to sort of solidify your knowledge and solidify your understanding of file versus directory permissions. Probably will be useful for you in studying for the midterm. Summarizing things here, we looked last day at users. We saw that at least the local users on a system are stored in the etc password file, and their passwords are stored in a separate file called etc shadow, which is accessible only to root. We saw that local groups were stored in etc group, and we saw the notion of a user private group, where when I create a user for someone, a user account, it also creates a group of the same name, and that's called their user private group. We saw that Linux divides the set of all system users into 3 sets, so user, group, and other. Took a look at the different permission bits, read, write, and execute, or we now understand it's also traverse for directories. Saw the chmod command, and that we can represent permissions as either octal or symbolically using the UGOA notation. Saw recursively changing permissions with chmod -r. Default permissions, again, for files, it's going to be 666, 777 for directories. But because the default UMask on most systems is 022, it further gets restricted from there. And you can restrict it even further if you want by setting your own UMask. And then, of course, we saw the differences in the different permission bits for files versus directories. Again, a little cheat sheet for you there to help you in your studying. And that wraps up topic 8.